I'm going to make a quick sketch for the graph of the function f of x equals x over 2x plus 5. First thing to look at are vertical asymptotes. They're going to occur when the denominator equals 0 and the numerator does not. So we can solve that equation, 2x plus 5 equals 0. We get a solution of x equals negative 5 over 2. And that clearly is not going to make the numerator equal to 0 because x equals 0 when x equals 0. So that means this will be a vertical asymptote. So I can start thinking about the graph, plotting some information here. Let's say this is negative 2, and I go over a little bit, this is negative 4. So we're going to have a vertical asymptote right here, just a little beyond negative 2. Now that's technically not really part of the graph, so I drew a dotted line and not a solid line to represent that. The graph I'll draw in a solid line. The second thing to think about are horizontal asymptotes. And those occur as the x values get really big or really small. So I want to think about x values that are way over here, really big values, or values that are very small over here. And to think about that, we can focus on the degree of the numerator and the denominator. And what you'll notice with this function, the degree is the same. And when the degree is the same, I want to look at the ratio of the two lead coefficients. So I have 1x in the numerator, and I have 2x in the denominator. And so the lead coefficients form a ratio of 1/2. And we do that because the degree is the same. If the degree is different between the top and the bottom, then we have to think about it differently. And one way to think about why that is true, why this is going to be our horizontal asymptote at 1/2, is because if you think about plugging in really big values for x, either on the positive side or the negative side of the number line, if we plug in really big values, this plus 5 in the bottom is not going to matter very much. Right? If I plug in 1,000,000, I get 1,000,000 over 2,000,005. And so that 5 is going to be way down, after a whole bunch of zeros, and it's not going to affect the division of those two big numbers. So we end up with a horizontal asymptote at 1/2. So again, let me say if this is positive 2 and positive 4, the horizontal asymptote of 1/2 is going to be pretty close to 0, but not quite 0, a little bit above 0. Again, that's a dotted line because it's more of a guide to the function and not actually part of the graph. As an equation, we would write for the horizontal asymptote, it's a horizontal line, so the equation of that asymptote is y equals 1/2. And finally, from seeing some examples of this already, you may recognize we're going to get a function that kind of swoops in one way or another. And we want to make sure we end up swooping on the right side of the asymptotes. So let's plug in a value or two. In particular, we could see what happens at x equals 0. So at x equals 0, the numerator equals 0. The denominator equals 5. So when x equals 0, we get 0, 0. We get a y value of 0 as well, because 0 in the numerator of a fraction means that the whole fraction is going to be 0, as long as the bottom is not also equal to 0. So this is going to be one of the points on our graph, right here, at 0, 0. And as values get bigger and bigger and bigger, we can see because of that plus 5, as values get bigger and bigger and bigger, we're always going to stay slightly below 1/2. We're going to get really close to it, but we're going to stay slightly below 1/2. So now let's take a look at what's going to happen as we get closer to that vertical asymptote. It feels to me like we're going to go down along that negative asymptote because we're already below the horizontal asymptote. So it's not impossible to cross horizontal asymptotes, but we don't do that very often. And so, but to check, let's see if we do go down. So as we get closer and closer, we can plot some other points and see what happens. If I plug in -1 for x, if I plug in -1, I get -1 over +3, so that's going to be negative. Down here a little bit. If I plug in -2, I get -2 up top, and -4 plus 5 in the bottom, so that's going to be down at -2. We're going to be down even a little further, down at -2. When x equals -2, y also equals -2. So yeah, so indeed we are going to drop down along that asymptote, and we can see that by plotting a few other points. We're going to be at -1/3 when x equals -1, and we're going to be at -2 when x equals -2. And then let's say one more point, if we look at -4, -4 is going to be negative up top, but if I plug in -4, I get -8 plus 5, so it's also going to be negative on the bottom, so overall we get a positive value, a value of +4/3. So at -4, we're going to be at +4/3, so that's going to be up here a little bit. At -3, similarly, we're going to get -3 over -1, because -6 minus 5. And so at -3 as well, we're going to be +3. And so we have a graph that swoops up this way. And there we have it. That's a pretty good graph of this function. I encourage you to take some time and work on your own to try to create a graph of the function g of x equals 4x plus 12 divided by x minus 7. It'll look a little bit similar. There'll be one vertical asymptote, one horizontal asymptote, but this time it won't cross the origin. There'll be separate x-intercepts and y-intercepts. I hope you enjoyed the video. Thanks for watching.